When you arrive in lab this week, you're going to find that the board has already been partially populated for you, as usual. We have over here on the left a dip switch, a little bit more sturdy than some of our other dip switches because we're going to be using it quite a lot. And we have another dip switch. I'm referring to the left dip switch as A, input A, and the right dip switch as input B. Now, of course, remember that if you're working with any kind of switch, you always take the signal between the switch and the resistor. So this is where you're going to be connecting the inputs to. We have here two different 4-bit adders. What we want to do is we want to do 8-bit addition. But to do 8-bit addition, you can have two 4-bit adders. You just have to take the carry out of the lower, least significant part and carry it in to the carry in of the upper part. In fact, you could have a 12-bit adder, you could have a 16-bit adder. It's pretty much limitless as to how many bits you could have. Now we have here a bar LED, which is going to be used to display the results. Of course, you're going to connect the bar LED on top so that current will flow through the LED, through the resistor to ground. And I've got 8 bits here. I've actually shaded out the 9th and 10th bits here so that you don't get confused. What you want to do is take the 8-bit output of the adder and you want to send it into the 8 LEDs on the right. I also have a separate LED here, which is used to represent the carry out, because there's going to be a carry out of the most significant half, and that carry out should go to this LED, so as to sort of distinguish it from the other 8 bits. It's important, but it's not always important, as we're going to see in the demonstration here in a second. So for right now, we'll just take it to a separate LED. The carry in of the right half should be 0 because we don't have anything coming in to the right half. And I've pre-wired the ground and power to each of these chips, and I've pre-wired the ground and power to the switches as well. These wires right here are simply to connect the red stripe on top to the red stripe on bottom and the blue stripe on top to the blue stripe on bottom. And in this particular breadboard, the left and right halves are separated, so I've had to include 2 sets of these wires. It may be that you'll only have 1 set of these wires on your case, depending on whether or not the 2 halves of the breadboard are connected to each other. And here's what the circuit looks like after you've fully wired it up. You can see that all of the inputs here on the left, which I'm referring to as input A, are being distributed across the 2 adder chips. All of the inputs on the right, which I'm referring to as input B, are also being distributed across the 2 adder chips. And the outputs of those adders are these 8 bits right here that are being used to drive this bar LED, as well as 1 extra bit right here, which is being used to drive this green LED. And this green LED, I've separated it out because it's the carry out. So sometimes the carry out is part of the output, and sometimes the carry out should be neglected. And so I've just separated it for that purpose. Now, to be able to show that this is working properly, let's go ahead and look at a quick example problem here. So I've got 100 plus 125 yields 225. So let's go ahead and plug the 100 in on the left. Now the nice thing is that you can read the first input here on the display because we're adding 0 to it, so it doesn't really change it. And then let's put the 125 in on the right. And if I've done my work properly, 1110001, 1110001. So 100 plus 125 is verified to be 225 according to the binary adder. That one was pretty straightforward. Let's look at a bit more detailed example, a bit more complicated example. Here I have 200 plus 250 should yield 450. Let me go ahead and zero these out. Don't want to have any of the leftover results from the previous calculation. Okay, so they're all zeroed out. Let's wire in 200 on the left. And then I'll wire in 250 on the right. And the result on the main 8 bits should be 11000010, 11000010. But then there's also this carry out bit right here, and that carry out bit is indicated by the lit separate LED over here. So we have to count that bit because the number that we're trying to calculate is greater than 255. 255 is the highest number that we could represent with 8 bits. But of course, if you're adding 2 8-bit numbers, you can get a 9th bit. You can get a number that's higher than 255. It can go up to 511 in this case, 512. So we have 450. That's going to need to use the carry out bit. So So that's addition, but in our lesson we also talked a little bit about subtraction. Subtraction is really still the same addition hardware. It's just that we need to negate one of the two numbers. And so remember that if you're going to negate a number, you're going to use 2's complement arithmetic, and that means that you need to invert every bit and add 1. That's just a brilliant shortcut for calculating the negative of a number. So here's 100 minus 50 yields 50. So this is the 50. We have to invert every bit. So 0011 becomes 1100, 0010 becomes 1101, and we have to add 1 to that. And so we get this result right here, and that corresponds to the negative 50 that I have right here. So just by coincidence, we had both positive and negative 50 here. Otherwise, I would have had to have looked up a third number. So let's see if this correctly is calculated by our arithmetic circuit. So I have 100 on the left. So that'll be there. And over on the right now, negative 50 is this number right here. And if I've done my work correctly, I should get 0011, 0010, 0011, 0010. And you might say, hey, that carry out bit is lit. So what's that mean? Well, if you're doing subtraction in this circumstance, carry out bit doesn't mean anything. You should just ignore the carry out bit, which is why I have separated it out from the rest of the bar LED. You might say, well, that's confusing because sometimes you have to count the carry out bit and sometimes you ignore it. And I would say, yes, it is confusing. It's one of the things, it's called overflow. And overflow is something that you're going to learn about next year when you take a full course or two in digital logic design. That's going to be something for your sophomore year. We don't want you to learn everything your freshman year, or else you're going to be bored for the rest of your time here in college. So let's zero this one out again, and let's zero this one out, and there we go. And now for the last thing, I'm going to do 47 minus 77, which should yield negative 30. And I've done the arithmetic here to calculate both negative 77 and negative 30. To do that, you have to first of all figure out what is positive 77 and positive 30, then invert every bit and add 1. And so I've done that arithmetic over here, and that's what's shown up in here. So now let's see if it works correctly. So 47 should look like this. So there's 47, and then I'll do negative 77. And if the work has been done correctly, we should get 111, 000, 10. We have 111, 000, 10. And so we've seen that not only can we do addition, we can also do subtraction as long as we understand the rules of 2's complement arithmetic. So of course, if you got this number, you would need to invert every bit and add 1, which would convert it back to positive 30, and that's how you would discover that the result had been negative 30.